Okay, so this is called blocks in equilibrium. Okay, so we have block A, which weighs 60 newtons. The coefficient of static friction between the block A and the surface on which it rests is 0.25. The weight is 12 newtons. There's another box or another block called W, and it weighs 12 newtons. And the system is in equilibrium. In equilibrium means nothing is moving, so that means everything is at rest. It means there's no acceleration, there's no velocity. It's just sitting constant. So that's what when it says the system is in equilibrium, that means nothing is moving. Find the friction force exerted on block A, and then find the maximum weight W for which the system will remain in equilibrium. So what we're going to do here is I have this thing kind of sketched out. Okay, so here's block A, and then here's block C. Block A is 60 newtons. Block C is 12 newtons. That's their weight is 60 newtons and 12 newtons. Okay, A is sitting on this shelf here, and there's a coefficient of static friction, which is 0.25. Okay, that's the friction between A and the table. So as A moves back and forth on the table, that's the coefficient of static friction, 0.25. Now there's a wall over here. There's a wall, and there's a rope. So the rope is attached to A, and it goes to this point B, and it goes up to the wall and is attached there, and then it comes back down, and it's also attached to C as well too. So this rope is attached to A, to B, to the wall, and then down here. Okay. Now the rope has tension in it. So let's call this part T1. Tension 1 is this string. And we'll call this string here T2. And then we'll call this one T3. Okay? So those are the three tensions, the three string segments. And then, of course, you can see that there is a 45-degree angle right here between the horizontal and T2. Okay, so what we want to know is what is the force, the static force, due to friction right here. So this, you can see this weight, right? It wants to pull down. It wants to pull down, which is going to cause A to go this way. It's going to cause A to go this way. So if A goes this way due to this tension, then that means the frictional force has to be pulling in this direction, right? So that's what it wants to know. Fs is what is this force in this direction right here. Now remember, also it says this thing is currently in equilibrium. That means nothing is moving. C is not moving, A is not moving, nothing's moving. But the question is what weight could you put on here? What weight could you add to C, or could you make C, so that it actually starts to pull this down and then A starts to go this way? What weight does it need to be? Okay. Now, obviously, you can say 1 billion pounds or whatever, 1 billion newtons. Now, what's the minimum? What's the minimum weight required to break this thing loose and then make the whole system start to go this way? Okay, so the best way, of course, to solve one of these problems, obviously, is a free body diagram. And so what we're going to do is we're going to start off with A first. Okay. And yeah, so we have A. This dot represents the block A. And A has, well, it has weight, right? Pulling down on it. And this weight is 60 newtons. And also, due to Newton's third law, because these two things, A is pressing upon, let me just change it to this, because A, this object is pressing down on this table. The table is also pushing up in the opposite direction. Okay, that's Newton's third law. Okay, so that's great. So what we'll do here is then that's called the normal force. Now, we have the weight pulling down 60 newtons. The question is, what's the normal force? Well, is this thing, is A moving up and down? No, it's not. It's not. It will only move, I mean, it's not moving at all, but even when it does move, it's going to move left to right in X. It's not going to move in Y. So if it's not moving in Y, that means this and this have to be the same because the forces have to be balanced. If the forces are imbalanced, that causes acceleration. So N has to be the same as W. Okay, so it has to be 60 newtons. If it wasn't, it would be accelerating, and it's not. So then the next question is remember here, this is my static friction due to static, the frictional force due to static, and of course over here we have tension, the tension in the rope, and this is called T1. So this is the tension, and remember in part T1. Remember there's this part T1, tension here T2, tension here T3. So we're at T1, okay? Because this is block A. Now FS, friction due to static. What's that? Well, that's the coefficient of static friction times the normal force. And that's 0.25, which we already had up here, 0.25, and the normal force is 60 newtons, so 0.25 times the normal, 60, equals 15. Sorry, let me do that again. 15 newtons. Okay, let me highlight these guys. So there's this one, there's that force. There's this force. Actually, let me go back. Change it. Oh, maybe I'll make it yellow. So there's that force, and there's that force. Now, this thing is not moving, so you could actually say T1 is 15. Maybe I'll just do it just for the heck of it. So this is also 15 newtons. Okay. You're like, how do you know that? Because remember, the system is in equilibrium, meaning it's not moving. Okay. So yeah, so you could say that. And so there you go. So now I've solved A. These are all the forces on A, 60 on top, 60 on bottom, and then 15 to the left and 15 to the right. So everything is nice and equal. It's not moving. And it's true, it's not moving. Now something I want to really bring up here. This 15 newtons, see this 15 newtons right here? This is actually the maximum force that can be applied to this object, okay? The maximum force. So T1, meaning, this is what I mean. Let's imagine T1 was 1 newton. Let's imagine T1 was pulling in this direction, just 1 newton. Well, what that means then is that the actual force over here is 1. So because remember, nothing's moving. So if this happened to be 1 newton in this direction, it also has to be 1 newton in this direction. If it was 2, it'd be 2. If it's 3, it's 3. If it's 4, it's 4. Because this can't be, let's say, 4 if this is 1, right? You're like, oh, if this is 4 and this is 1. No. If that were true, it would accelerate in this direction. But friction doesn't cause acceleration, does it? Does friction cause acceleration? No. So it couldn't be that this is bigger than this. Okay. So friction doesn't cause it to accelerate. So whatever this is, it mirrors it. So if this is 1, this is 1. If this is 2, this is 2. If this is 3, this is 3. But up to a maximum of 15. This is the maximum. So if this is 15, then this is 15. But if this is 16, he can only be 15. So if this is 16, 15 is his maximum, right? 15 is his maximum. So guess what happens? So now that this is 16 and 15 is his maximum, it will start to accelerate in this direction, right? It'll start to accelerate in this direction. Because 15, when you see this number here, that's the maximum it could be, okay? Okay, great. So we have that. Now, let's go on to, I want to actually do C next. C is the weight, So let's model it. So this is the weight right here. And it, as you can see, only has 2 forces on it. It has tension on the top, or T3, right? T3, and has weight on the bottom. And we already said this is 12 newtons. And so because this is 12 newtons on the bottom, and it's currently not accelerating at all, that means this is also 12 newtons, right? Okay, so let me just color that one as well. So we have this one. and this one. And this is the weight block C. Great. Next one is the trickiest one, and that's B. That's like the knot in the middle. Okay. And so it has T1 going this way. It has, this is T1. It has T3, tension, T3 going down. And it has T2 going right there. Okay. And you may remember that this is 45 degrees. 45 degrees. Okay. So what we can do is we can break this up. Let me just change it. Sorry, let me change it to this guy. Into this component, let's say, and this component. Okay. So the red is T2 times sine, because 45, this is the opposite, so it's sine 45. And the blue is T2 cosine. Whoops, cosine 45. Okay. Now here's the thing. T3, which is right here, is 12. So if that's 12, then this T3 also has to be 12 newtons. Okay? This also has to be 12. And if that's true, that's pulling it down. If that's true, then this also has to be 12 newtons, right? Because this is the because this is the downward. See that? That's the downward, and the upward. This is the down force. This is the up force. They have to balance each other. So because this is 12, this also has to be 12. So T2 sine 45 has to be 12. Has to be 12. Now what you could do is you'd be like, okay, what's T2? Well, what you could do is take T2 equals 12N divided by, basically just take the sine 45 and put it at the bottom here in the denominator. So it's 12N divided by sine of 45, and so that would be T2. Now you would have T2, okay, which is fine. But it actually happens here. What actually happens here is that because this is 45 degrees, sine and cosine happen to be the same at 45 degrees, so you could just go ahead and say 12 newtons. Okay, so this actually also happens to be 12 newtons because it's at 45 degree angle. So they're the same. Okay, and so that's basically it. So now here's where it gets interesting. Because T1 is here and here, you can kind of, they're internal nodes, right? You can kind of get rid of them. And T3, see this? You can kind of get rid of that. You can kind of get rid of that as well too. And so really what you have is, at the end of the day, you have this 15 newtons maximum of static on one side, and on the other side you have this, the T2 cosine 45, right? So this T2 cosine 45 is pulling in this direction, and the static friction is pulling in this direction. The tensions are just internal. They're just internal. But what's actually driving it? What's actually driving it is the tension here. T2 cosine 45 is pulling this way, and then the static is kind of pulling in this opposite direction. So the question here is what's the static friction? It's actually 12. It's actually 12. Now remember here I said, you're like, oh no, it's 15. No, that's the maximum it can be. It's whatever is over here. It mirrors whatever is actually being pulled. And because this thing is actually pulling 12 newtons, that's what it's actually pulling, that means that the static friction is actually 12. It's not 50. Remember, 15 is maximum. But if this weight, see, the weight is what's pulling it down, the weight is 12. And so if this weight were 13 right here, if the weight were 13, this would be 13 as well too. If this were 13, then this would be 13. If the weight were 14, then this would cause this to be 14, which would cause this to be 14, okay? It's sort of like a chain reaction. But the maximum weight is 15, because if the weight becomes 15, then this becomes 15, and then this is 15. So they're all maxed out. But once this becomes, let's say 16 newtons, then this becomes 16 newtons, but 15 is the maximum. It can't go more than that. So it'll start to move, right? So once this becomes 12 is fine, 13 is fine, 14 is fine, 15 is fine, and then greater than 15 is bad. So let's say 16. 16, it's going to become too heavy, and it's going to cause this thing to come down, and this thing's going to come over, and it's going to fall off the thing, okay? Anyway, so just in recap, what I want to say is these internal nodes, like these T1s and T1s, you can get rid of them. Or the T3s and T3s, you can just get rid of them. Because they're opposites of each other. This is like a positive T1, this is a negative T1, this is a positive T3, negative T3. They just cancel each other out, so just get rid of them. It just makes the algebra simpler to do. And then the other thing is when you're computing static friction, is when you compute it, which is your coefficient of static friction times the normal force, this is the maximum it can be, okay? So if someone is pulling at 1 Newton, this is not 15 newtons, because that would cause an acceleration. There's no acceleration here. So if someone's pulling at 1, this is 1. If someone's pulling at 2, this is 2. This is the maximum it can be. So once they pull past 15, let's say 16, now it's going to start to move, okay? Anyway, that's it.